Hello, my name is Jim Kasting, and I'm a professor of geosciences at Penn State University. And I'd like to talk to you today about the Earth's early atmosphere and its role in the origin of life. So the talk is short, but I've divided it into three parts. I'm going to talk first about strongly and weakly reducing atmospheres and what those terms mean. Then I'll talk very briefly about the faint young sun problem, and spend most of my time on topic 3 there, the origin of life, and with specific focus on thermodynamic free energy considerations. All right, so if we think about historical theories of the origin of life, a lot of it traces back to Alexander Oparin over in the then Soviet Union, who wrote a book in 1924 about the early Earth and the origin of life. And that book was in Russian. It was reprinted in English, however, in 1938. And that book is still a reference that one can get hold of. So in Oparin's view, the early atmosphere was a mixture of highly reduced gases that contain a lot of hydrogen. And for instance, methane, CH4, and ammonia, NH3. And that is similar to how carbon and nitrogen appear in the atmospheres of Jupiter and Saturn. And so Oparin thought that this would be a good venue for forming prebiotic compounds, and that idea caught on. In fact, the thing that really made it catch on was a series of experiments carried out 20 years later by Stanley Miller, working in Harold Urey's lab at the University of Chicago. This is the famous Miller-Urey experiment, where Miller, as part of his PhD thesis work, created highly reduced mixtures of gases and then ran spark discharge through them, simulating lightning in a highly reduced atmosphere. And the results of these experiments were widely publicized. They produced amino acids, all sorts of compounds that are building blocks of life. And Urey also agreed with Oparin's reasoning. In fact, Urey extended it by saying that Jupiter and Saturn are so big that hydrogen doesn't escape from their atmospheres, and therefore on the early Earth, before hydrogen had had time to escape, our atmospheres would have looked like those of Jupiter and Saturn. However, at the same time that Stanley Miller was doing his experiments at the University of Chicago, a geologist named William Ruby was writing papers about his theory of the early atmosphere, and that was quite different. Ruby was a geologist, and one of the things he did in his career was to look at, measure the compositions of volcanic gases coming out of the present Earth. And what he noticed is that those gases are not highly reduced. You see very little methane or ammonia coming out from surface volcanism on the Earth. Instead, the carbon is mostly in the form of CO2 with a little bit of CO. Hydrogen comes out mostly as water, H2O, with a little bit of H2. And you don't get much ammonia at all. We think that nitrogen comes out as N2, although that's hard to measure against the background of the N2-rich atmosphere. So why is that? Well, it's because the Earth's mantle today is relatively oxidized, and relatively is the key word there. It's not oxidized enough to emit O2. There's basically no O2 in volcanic gases, but it emits carbon in sort of a neutral oxidation state as CO2, and nitrogen is N2. And why is this? Well, that's a complicated story, which I'm not going to have time to dwell on, but the Earth's mantle self-oxidizes during the accretion process, we think. You form a magma ocean from the energy of all the impacts, and then at the at depth in the Earth's mantle, the ferrous iron, Fe+2, disproportionates. Some of it gets oxidized to ferric iron, some of it gets reduced to elemental iron. The elemental iron sinks to form the core, and some of that ferric iron, oxidized iron, is left behind in the mantle. So we think now that the Earth's early mantle was also oxidized, maybe not quite as much as today because there are other processes that can oxidize it later, but we don't think that the Earth's mantle was ever outgassing highly reduced gases. All right, so today Ruby's logic has prevailed. One of my academic mentors at University of Michigan, James Walker, was actually a key person in pushing Ruby's ideas. And so we now think that the early atmosphere was what we call a weakly reducing atmosphere. Here's a diagram that I published in a paper in Science in 1993 that shows the major constituents in a weakly reduced atmosphere as calculated with a one-dimensional photochemical model, which is one of the tools that I've used in my own research. And the calculations here were for an atmosphere with 1 bar of surface pressure. That's just an assumption. We don't know what the pressure was in the earliest atmosphere. But notice that it's got about 80% N2, 20% CO2, which of course is a lot more CO2 than you have in the present atmosphere. Present atmosphere has about 400 parts per million of CO2, but the early atmosphere must have had more CO2 to keep the Earth warm in the face of the faint young sun, which I'll talk about in a moment. There's a little bit of H2 molecular hydrogen in this model. That is basically calculated by balancing outgassing of H2 and other reduced gases against escape of hydrogen to space. And this was shown by Jim Walker many years ago. And then notice also that there's O2 up at high altitudes in this atmosphere that is produced by photolysis of CO2, making CO and O, and then the O atoms recombine to form O2. So that gives you a source of O2 up in the stratosphere, but that O2 is consumed by reactions with reduced gases down low. And then the other gas that I'll point out here, and I will come back to and talk about in more detail, is carbon monoxide, CO, which is a little less abundant than H2 in this atmospheric model, but I'm going to argue that it could have been much more abundant in some models of the early Hadean atmosphere. All right, so let's talk briefly about the faint young sun problem. We think that the sun was about 30% less luminous when it's formed, and it's brightened more or less linearly with time. So why is this? Well, that's because the sun is producing its energy by nuclear fusion. It's converting hydrogen to helium in its core. As it does so, the core becomes denser. The sun is a self-gravitating body, so it collapses when the core becomes denser. That causes the core to heat up, and then the higher temperature causes the fusion reactions to go faster. So here is a diagram that I published back in 1988. It was really very similar to a calculation that had been published in 1972 by Carl Sagan and George Mullen. And what this diagram shows is two things, really. The solid curve is solar luminosity relative to the present. That goes with the scale on the right. The two dashed curves, the lower one is T sub E, the effective radiating temperature that one can calculate by balancing input of energy to the Earth against export of energy. And then T sub E, the upper dash curve, is the effective surface temperature calculated with a climate model. And the calculation here was done just like Sagan and Mullen did it, by assuming that the Earth's atmosphere had essentially the same composition as it has today. It had the two main greenhouse gases today are water and carbon dioxide. And this atmosphere, this set of calculations had present day levels of carbon dioxide. So what you find, because as you go back in time, the sun was less bright, you find that the surface temperature, the average surface temperature drops below the freezing point of water prior to about 2 billion years ago. That's the same result that Sagan and Mullen got. And geologists know that that can't be true because the Earth would have frozen, the oceans would have frozen over entirely, and yet there's evidence for liquid water going back to at least 3.8 billion years. So we now think that CO2 builds up when the climate gets cold, and so the Earth's early atmosphere was probably rich in CO2. All right, so let me switch gears a little bit and say what I think these implications are for the origin of life. So the origin of life it's a fascinating topic. It's also a very difficult one. And one way of classifying theories of the origin of life is shown on this slide here. There's sort of three different ways of thinking about it. One is information first, or RNA first. You have to have molecules that can be made into genes to record hereditary information. Then there's another idea that's become popular in some circles in recent decades, and that's metabolism first. You need a source of free energy, not just for the origin of life, but to drive metabolism once life gets going. And then a third set of theories might be called vesicles first. You need some membranes or something to separate out organisms from their environment so that they can evolve. And the thing that makes the origin of life difficult is that you really need all three of these things, and somehow they all need to happen at the same time, and people are still trying to understand how that might occur. So let me talk a little bit about, I'm going to focus on the metabolism first here, just because I have only a limited amount of time to talk. And I want to focus here on environments and ask the question of where did the origin of life occur? Was it in a surface environment, or as some people have proposed, in a submarine hydrothermal vent environment? All right, so there are proponents of the hydrothermal vent theory, and Mike Russell and his colleague Hall have been two of the outstanding proponents of this. So they've proposed that life evolved in alkaline hydrothermal vents along the mid-ocean ridges. So these are not the very hot black smokers at the ridge crest, but they're the cooler, high pH vents that occur off axis. And one of their motivations is that there's a lot of free energy, thermodynamic free energy, that's available there by reactions like the one that's shown in blue here, taking 2 CO2s plus 4 H2s and making acetate, written here as acetic acid, CH3COOH plus 2 H2O. And you can also make other organic compounds that that's thermodynamically favorable, or you can make methane. There's also free energy available from pH gradients within these vents, and Russell and Hall consider both of those, and they come up with free energy gradients that are in the range of 40 to 80 kilojoules per mole, which is really quite a lot of energy. The energy needed to synthesize ATP from ADP is about 35.6 kilojoules per mole. So that's one of that could have been a driving force for the origin of life. Now, what I want to point out here is that free energy is also available in the surface environment. So let's go back to this diagram that I already showed you. This atmosphere has a little bit of CO in it, and a little bit of H2, and a lot of CO2. But CO is a high free energy compound. As I already said, the CO2 is photolyzed by solar ultraviolet light, making CO and O. And so that energy of that ultraviolet light went into the products. So when you recombine CO with H2O to make CO2 and H2, that reaction is downhill thermodynamically. And so under standard state conditions at 25 degrees C and 1 bar pressure for all of the gaseous constituents, you get about 20 kilojoules per mole from that reaction. But now thinking about, and that reaction has a name. It's actually very well known. It's called the water gas shift reaction. Now, let's think about that a little bit more, because the free energy of the reaction is not in the natural environment. It's not just the standard free energy, because the constituents, the gaseous constituents, are not all at 1 bar partial pressure. So the free energy in the environment is delta GR, and that's delta GR0, the free energy of the standard state, plus RT ln Q, natural log of Q, where Q is the reaction quotient, and that is the product of the products divided by the product of the reactants. So if you take this sort of generic atmosphere that I've shown in the diagram and compute RT log of Q, you get about 3 kilojoules per mole. You add that to delta G0 and you get minus 17 kilojoules per mole. So that reaction is exothermic, but not highly exothermic. However, the atmosphere that I've been showing you is really a hypothetical early Archean atmosphere, say around 3.8 billion years ago, long after the Earth formed. And many of us think that life actually originated during the Hadean eon, long before that. The Earth was formed at 4.6 billion years ago. So you had about 0.8 billion years before you get to the Archean, right? And during that Hadean, the Earth was not a quiescent environment. You had impacts coming in, the tail end of accretion. There were high energy particles coming from the young sun, which was very magnetically active, and that's something we're studying right now. And so we have found in our models that during that time, you could have been breaking CO2 apart much more effectively and making a lot more CO. So in fact, in some of our models, CO is roughly equivalent to CO2. So if you put that into this atmosphere, make CO equal to the CO2 concentration, then RT ln Q is minus 20 kilojoules per mole, and the free energy from that water gas shift reaction is about minus 40 kilojoules per mole, which is comparable to the energy that is available in the hydrothermal vent environment. So one other thought before I close here is that are there any advantages to trying to originate life on the surface as compared to hydrothermal vents? We think that there are two. One is that temperatures may be cooler on the surface than they are at hydrothermal vents. The vents are almost by definition hot. They're not the really extremely hot temperatures of the axial hydrothermal vents, but they're still around 50 or 60 degrees Celsius. And organic compounds like nucleic acids and amino acids don't last long at those temperatures. They hydrolyze. So if you have a warm little pond at the top, but maybe not too warm, if there are regions of the Earth like the polar regions today that are cool, then you could do these reactions, try to form life at lower temperatures. And the other thing that works in favor of surface environments is that vesicles today, the membranes that hold organisms together, today they're made of complex phospholipids, and there are organisms that live in seawater. There are lots of organisms that do that, and there are also organisms that live at high temperature. But the earliest organisms probably had simpler lipid membranes, and simple lipids are actually unstable in the presence of salty water. So especially divalent cations like magnesium and calcium can destroy those lipids. So in the mid-ocean ridge hydrothermal vent environment, you can't avoid salt water, but if you're trying to originate life in the surface environment, you might be able to do that in a freshwater pond. And so that may be an advantage for the surface environment. All right, then, in summary, Earth's early atmosphere was a weakly reduced mixture of CO2, water, nitrogen, and a little bit of H2. CO2 was much higher than today because you would have needed it to counteract the faint young sun, and there are feedbacks that would have made that happen. CO levels, carbon monoxide, could have been very high during the Hadean, and that's what I've spent most of my time on. And so that CO can provide a source of free energy for the origin of life. And it works best in the surface environment, which has other advantages, the cooler temperatures and the availability of fresh water that I just mentioned. So thank you. There's references at the end if you want to follow up and read some of the papers on which this talk is based. Bye-bye.